You know that feeling, right? You've got a bunch of really good options in front of you, and you have to pick just one. How do you really know you're making the best choice? Well, today, we're going to look at a super smart method called the new weighted sum model that gives you a clear, logical way to find the absolute best option. Let's get into it.
So let me ask you this. Think about it. When you're picking, say, a new laptop, do you want the one that's kind of good at everything? Decent screen, okay battery, fine keyboard? Or do you want the one with the absolute best processor because you know that's the one thing you care about most? It's a classic problem.
And this is what's so cool about this model. It basically says, why choose? You don't have to. It builds a system that really values a strong all-around performance, but it has this really clever backup plan to make sure your top priorities are always respected. Let's see how it pulls that off.
All right, so let's get our hands dirty and see this thing in action. We're going to use a concrete example from the source paper. We've got 5 different options, and we're judging them against 4 different criteria.
Okay, so here are the players. We've got 5 alternatives. You can think of these as anything: job offers, car models, you name it. And they're being scored on 4 criteria. Those are the things that matter to us. Now here's the most important part. These criteria are already in order. C1 is our #1 top priority, C2 is second, and you get the idea. That order is absolutely crucial.
So how do we even start to compare these things? Well, the very first step is to calculate something called a preference value. And this isn't just a raw score. It's not about how well an option performs, it's about how well it performs on a criterion that you've already decided matters.
Let's break that down. This preference value, which the paper calls EIJ, is really just one number that cleverly mixes 2 things: how good an option is at something and how much you actually care about that something in the first place.
And the formula for it? It's beautifully simple. Your preference value is just the weight of that criterion, that's its importance, the W, multiplied by the alternative's performance score, the Q. Now that Q score is normalized, which is just a fancy way of saying all the scores are put on the same scale, like 0 to 1. That way, you're not comparing apples to oranges. It's a perfect mix of priority and performance.
Yep, that's it. For every single alternative, against every single criterion, we're just doing these 2 simple things. We take its performance score and we multiply it by how important that whole category is. We do this over and over until we have a preference value for every spot.
Okay, so once we've calculated all those individual preference values, it's time to zoom out. We need to combine them to get one single overall score for each of our 5 alternatives. This is what we call the overall value, or V of A, and it's just the sum of all the preference values for that one option. You just add them up. You take the weighted score from C1, add it to C2, add it to C3 and C4, and boom, you get one final number for that alternative. And this big score is our first stop. It gives us our primary ranking. The alternative with the highest overall score is, on the surface, our winner. Simple, right? Higher's better. But what if it's not that clean?
And this, right here, is where the new weighted sum model really shines. It has a built-in answer for a really common problem, and it's an incredibly logical solution.
Here's the million-dollar question. What do you do if 2 of your options end up with the exact same total score? Is it a tie? Do you just flip a coin? This model says no way. Just imagine this. You've got alternative X and alternative Y. You've done all the math, and they both land at 0.634. It's a dead heat. A lesser model would just get stuck right here and call it a draw, but this model has an ace up its sleeve.
This tiebreak rule is the secret weapon. If those overall scores are tied, you forget the big score for a second. Instead, you zoom right in. You look only at their scores on your most important criterion, C1. Whichever one is better on C1 wins, period. And if, somehow, they're still tied on C1, you just move down the list to C2, then C3, until that tie is finally broken. Now, the source paper puts this a little more formally. It basically says one option is better than another if its big score is higher, or if the big scores are equal, you then check its score on that first most important criterion. This simple, powerful logic just flows right down your list of priorities until a winner has to emerge. All right, enough theory. That all sounds great, but let's apply this to our actual example and see who the winner really is.
And here they are, the final overall scores. As you can see, alternative A2 comes out with the highest value, 0.634. Now, in this particular case, all the scores are different, so we didn't actually need to use that special tiebreaker rule. But it was always there, waiting in the background, like a perfect safety net to guarantee we'd get a clear winner no matter what.
So based on those scores, here's our final, unambiguous ranking. A2 takes the top spot. Then we've got A1, A4, A3, and A5 bringing up the rear. There's no confusion, no ties left unresolved, just a clear, logical order of preference.
So let's just take a step back and ask, why is this method so good? What makes it so solid for making these kinds of complex decisions?
The real magic is in its two-level system. It rewards the options that are good all around with that big overall score, but it never, ever forgets what you said was most important, using your priorities as the final judge in any close call. It sees the big picture, but it also respects the details that matter most to you.
And one of its most powerful features is just how stable it is. The paper points out that if you add a totally new option to the mix, say alternative A6, it doesn't mess up the ranking of the original 5. That might sound like a no-brainer, but a ton of other models fail at this. They suffer from something called rank reversal, where adding a new, irrelevant option can suddenly make the old winner the new loser. This model doesn't have that problem.
And that's really the perfect thought to end on. Yes, this model gave us a clear winner, A2. But that answer is a direct reflection of the priorities we set at the very beginning. The framework is totally objective, but the inputs, the things you care about, those are all yours. So next time you have a big decision, the real question isn't just what are the options, but what really truly matters to you, and in what order.